Okay, so for the introduction or an introduction to statistical learning, the second edition, so we're on question 3A and 3B, and this is what I have up here. So we want to provide a sketch of a typical bias, variance, training error, test error, as well as irreducible error curves. And where this deviates a little bit from what is demonstrated in the book is this wants it all on a single plot. And then to explain why each of the 5 curves has the shape that it has. Okay, so like I said, the book shows some examples of this, but it doesn't have all in the same plot, and it shows it all at once. And so I thought that maybe we could just build this up, just one line at a time here. Okay, so so let's start filling in these curves. Let's see. So let's first start with the bias. Okay. Now, of course, we don't actually. So let me back up. So what we are going to show here is mean squared error. Now, there's going to be mean squared error that is both on the training set as well as the testing set. And so we'll fill both of those in time. But the first thing that we want, so again, what we have is some data, and we want to estimate a function f hat for that data, and that function is going to be incorrect. It's not going to perfectly fit the data, and that incorrectness, the errors in the model, can be broken down into bias and variance, as well as this irreducible error term here. Okay. So bias, let's get bias in here in this blue color. Okay, so the y-axis is just going to be the magnitude without units, really. It's going to be the magnitude of the error by any of these components, and the x-axis is going to be flexibility. So as we move to the right, flexibility is going to increase in the model. Okay, and so bias so what is bias? Again, bias is the model's inability to handle the complexity in the data. And so as we make the model more flexible, it can fit itself to the data better. Okay, and so at low flexibility, we have moderately high bias. Okay, there's nothing special about the level that I'm choosing here. It's arbitrary, just enough to draw these things in. And then as we move along, eventually we get out to infinite infinity, in which case there's 0 bias, okay? And we move from an area of high bias, let's see if I can draw this somewhat smoothly, to low bias. Again, the exact shape of this curve isn't important, something like that. The exact shape of the curve isn't important here. It's just a general trend that we expect to see. The actual shape of the curve is very much just going to depend on the function in the data. Okay. Now, next is variance. Okay. So again, how do we think about variance? We want to think about variance as so this variance here, not the irreducible error. We want to think of variance as how the model's outputs would change across different data sets, and not just arbitrarily different data sets, but data that was derived in the same way over and over again. Okay, and so we might think about this as taking a population and sampling from the population. And every sample we get from this larger population is going to be slightly different or something like that. Okay, so variance is going to start very low. So at very inflexible, very simple models, we have very low variance, and as we increase flexibility to maximum flexibility, we have very high variance. Okay, and again, the exact shape of the curve isn't important here. It is determined by the exact function and the exact data, but it might look something like this, something like that. Okay. So now we have our bias and our variance in there. Okay. And there's one more kind of component, and that is this irreducible error, okay, which is represented with the var epsilon here, okay? And irreducible error is error that we cannot get rid of by adjusting the flexibility of our model, okay? And so I'm just going to draw it at a level here. Its level, again, doesn't matter. This is just arbitrary where I'm drawing it. And it also doesn't, even though I'm going to draw it at about the level of maximum bias, these are independent things, okay? So we don't need to, yeah. So the relationship of the gray curve with everything else is just arbitrary, okay? Okay, so now what we have is mean. Well, let me get here. Okay. Well, now the total error is just going to be the sum of these three components. Okay, so I'll do my best to kind of fill this out. Okay, so if we're at minimal flexibility, okay, we start out with the amount of the error, the irreducible error plus the bias. Okay, and so we're actually going to be, so the gray curve plus the blue curve is going to be somewhere up here. Okay, and now at the other extreme, we still have the irreducible error, but now bias is driven to 0, but variance is very, very high. Okay, so I'm actually going to be off the screen, unfortunately, but I'll just say that it's here. Okay, it would actually be higher than that. And then let's maybe pick this intersection point. So again, we have to go to the irreducible error, and then the blue curve plus the orange curve. Okay, something like that. And then just for good measure, I'm going to guess that the minimum error is taking place somewhere here. So it's going to be irreducible error plus bias plus variance. Now this isn't very exact by any means, but what's important is that the mean squared error is just going to be the sum of the other three components at each point. So it might look something like this. Okay, that's again not super great. Okay. Now we also, so finally, we need to discuss the difference between training error and test error. Okay, so the MSE that I've drawn here is akin to test error, and maybe one way that I think about this is why is this the test error? Well, it's because it is necessarily including the component of variance, and the variance only makes sense if we have multiple data sets. Okay, so I need to draw another error here for the error in the training data. I'm going to use a dotted line for that. Okay, so the training error is going to go down in a similar pattern, but it is just going to continue to go down as we add flexibility, right? Because as we add parameters, and in fact, as we add once we max out at one parameter per data point, we fit the data perfectly, and so we drive the error down all the way to 0.